In this lesson, we will talk about how to find volume of a three-dimensional object rather than just area of a two-dimensional region. In this case, we will be looking at a two-dimensional region which is then rotated about an axis of rotation, an axis of revolution, often the horizontal axis or the vertical axis of the coordinate plane. It is possible to do it around other axes of rotation, although it does become more complicated to do so. Now, this, because it does result in three-dimensional figures, is a little tough to visualize. And there are other videos posted on our homepage that can give a better graphical representation of this than I can for some specific problems to get the concepts down. But in general, for most problems, we're going to need to actually draw the two-dimensional region in question and then indicate the rotation. So let's suppose, for example, that we have a function defined on an interval of the x-axis from a to b, continuous on that interval, so that we have a fully enclosed region, and then that region is to be rotated about the x-axis. In order to understand what's going to happen here, again, because the visualization of this is difficult to do, it's difficult to draw the three-dimensional objects, we're going to draw just one piece of it, and it's going to be based on the same concept as the Riemann sum. A Riemann sum subdivides the interval of the x-axis into different regions of, well, typically equal size. And then it bases the height of the rectangle in that region on either the right endpoint, left endpoint, or midpoint of the function value at either the left, right, or right endpoint or the midpoint. Traditionally, we use the right endpoint because algebraically, with the summation, it just tends to work a little cleaner. So the idea here, then, is that this rectangle, this single rectangle, upon rotation, is actually going to become, this rectangle, upon rotation, is actually going to become a disc shape. As it swings around, as that one rectangle swings around, it's going to become this flat cylinder, this disc shape. And instead of finding the area of the rectangle, we instead would be finding the volume of this disc. So let's remember how the area of the rectangle works. The area of the rectangle is the height times the base, where the height is given by the value of the function, and the base is given by the width of the interval, which, again, assuming that they are all evenly spaced, that would be delta x. So f of x of I is the height of the rectangle, and delta x is the width of the rectangle, the base of it. Upon rotation, then, the volume of the associated disk would come from pi r squared h. That's the volume of a cylinder, where the radius of the cylinder is going to be from the center of the circular cross-section to the edge of the disk, which is exactly the height of the function. The radius is the y value of the function. The height, then, of the disk, or rather, since it's flipped on its side, we would call it the thickness of the disk. The thickness of the disk is this dimension here. And that is the same as the width of the rectangle, the base of the rectangle, which means we still have delta x here. So the area of the ith rectangle corresponds to the volume of the ith disk, where the height of the rectangle becomes the radius of the cylindrical disk, and the base of the rectangle becomes the thickness of the disk. Thus, if the area of the region given by the Riemann sum from 1 to n of f of x sub I times delta x, where of course delta x is equal to the width of the total interval divided by n, and x sub I is the right endpoint of the ith subinterval. This will, when a limit is applied to it, result in the integral from a to b of f of x dx. Well, if we rotate this region around the x-axis, we produce a three-dimensional solid shape whose volume would be given by pi times the radius squared times the thickness of the disk, which, with a limit as n approaches infinity applied to it, would become the integral from a to b of pi times f of x squared dx. This is known as the disk method. In future lessons, we will also talk about something called the shell method. But for now, we have the disk method for finding the volume of a solid of revolution. Let's look at an example then. Let's suppose that we have the region bound by the graph of bound by the graph of f of x is equal to the square root of the sine of x on the interval from 0 to pi. And the x-axis. And that region is going to be rotated about the x-axis. Now again, it very much helps here to sketch a graph, to sketch the region in question. It's not strictly necessary to use the formula, but it does help a little bit. The graph can be obtained from a graphing calculator. Particularly for a graph such as the square root of the sine of x, which will produce a semi-ellipse, something along the lines of this. Now, it's not perfect, but it gets the point across. And the idea then is that any single subinterval here would have a rectangle on it, and rotation about the x-axis would turn this into a disk that would appear something like this, where the radius of the disk would be the sine of x, and the thickness of the disk would be equal to delta x, or dx, as we use more and more and more disks. Thus, the volume of this would be the integral from 0 to pi of pi times the square root of the sine of x squared dx. Literally, pi times the radius squared times the thickness. We can, if we choose, bring the pi out in front of the integral. But the square root of the sine of x, which is then squared, results simply in the sine of x, the antiderivative of which is negative cosine of x, and that will be evaluated at pi, and then subtracted from that would be the evaluation at 0. Again, this being a definite integral, the constant of integration, the plus c, can be omitted. This will then give us pi times negative cosine of pi minus negative cosine of 0. The cosine of pi is negative 1. And then we have minus the negative cosine, which turns into a plus, of 0, which is 1. The opposite of negative 1, of course, is 1. And we are left with 2 pi as our total volume. Now, the answers here are not going to be intuitive, because we're looking at a region that does not have an intuitive area, and then the revolution of that region to form a three-dimensional object is going to further ambiguate the result. And like the previous lesson, this can be checked in the calculator, but we have to understand that if you were to actually put the integral from 0 to pi of pi times the square root of the sine of x squared dx into the calculator to have it draw the region, it is not going to look like a three-dimensional object. Because if we put it in the calculator, it will graph a two-dimensional region. So the region sketched by the calculator, if we put this in, is not going to look at all like the three-dimensional object created by the rotation. However, the interesting thing is that this integral accumulates area at the exact same rate that the three-dimensional object accumulates volume. So an interesting thing here is that we're actually taking the concept of a three-dimensional object and we're evaluating its property of volume using a two-dimensional region. We're essentially projecting the multi-dimensional object into fewer dimensions where it's easier to work with. That underlying concept of what we're doing here is actually very crucial to how a lot of things are handled in physics, particularly when we're dealing with higher dimensional theories, such as string theory, which deals with upwards of 10 to 11 dimensions, depending on the exact nature of the string theory that you're looking at. There are several versions. But you might ask, how on earth is somebody supposed to handle the math with so many dimensions? And as it turns out, it is possible, depending on how the concepts align, it is possible sometimes to project the multi-dimensional, the higher dimensional equations and concepts into a lower dimensional space where it's actually easier to work with. And that's essentially what we're doing here. Let's look at another example, but this time we're going to look at a region that is revolved around the y-axis. Suppose the region this time, which we will call R, the region is bound by y equals x squared the x-axis, the y-axis, and to the line y equals 4. And then it will be rotated about the y-axis. I'm sorry, I suppose I should be a little more specific here. We do need to be a little bit more specific here because this function is mirror imaged on both sides of the y-axis. So we specifically want to look at this region inside there. And it is going to be rotated about the y-axis. Now, if we attempt to do this in the same way that we did before, that is to say with rectangles that are based on the height of the function in a vertical format, those rectangles would be oriented like this. But because we're not rotating about the x-axis, because we would be rotating about the y-axis, we would not get a disk out of this. We would get what's known as a cylindrical shell, which we are not quite ready for. We will get to that in a future lesson. And we don't have a formula for that just yet. Again, we will see that in a future lesson. So our alternative here is that we need to look at this. Of course, I just did that. We need to look at this in terms of y rather than in terms of x. What we need to do is integrate this with respect to y, so that our rectangles will go sideways. And then when we rotate them about the y-axis, we end up with our disks in an orientation that might look actually a little bit nicer, even if the variables have to be interchanged. We saw this in the previous lesson on area between two curves, where we had the option of orienting our integration to be with respect to y rather than with respect to x because it was easier. In this case, we don't have a choice at this time. In the subsequent lesson, we will find a way to deal with those cylindrical shells that I just described, but we don't have that just yet. And as we'll see, the cylindrical shell method may not be our favorite method of dealing with it. So it's nice to know that we have the option. For right now, This is our only option, to create our disks, but to do them with regard to y. So we're going to have to take our functions, in this case it's just the function y equals x squared, and we're going to have to invert it to give it x as a function of y. And that's simple enough to do. We just square root both sides, except for the fact that we would get a plus or minus in front of the square root of y. However, that is readily addressed by the fact that x has to be positive. That gets rid of the negative sign and allows us to keep just the positive. So in this case, instead of doing it with respect to x, our volume is going to be from y equals a to y equals b. And pi times the function of y squared times dy. As far as the limits of integration go, they work the same way they did when we found the area with respect to y, and they work the same way that they worked when we do it with respect to x. We integrate from the lowest possible y value we could draw the rectangle at, which is down here at the bottom at y equals 0, up to the highest place we could draw the rectangle at, which is at y equals 4. Our function of y is the square root of y. And this is actually fairly straightforward then. Like in the previous example, we can bring the pi in front of the integral. When we square the square root of y, we end up with just y. The antiderivative of which, of course, is y squared over 2. And this is simple enough to integrate, or to evaluate. We have 4 squared over 2 minus 0 squared over 2 for a final result of 8 pi. Once again, not an overly intuitive result, but something that can be verified using the calculator, at least to evaluate the integral. The assumption, of course, is that we wrote our integral correctly. So we need to be very careful about that, and that's why drawing the picture helps. Now, sometimes the rotation, or rather the region, is such that it actually produces a region that has a hole in the middle of it. For example, suppose we were looking at the region bound by the graphs of f of x equals x squared and g of x is equal to the square root of x. This region, x squared, would go thusly. And the square root of x would go something like this. And they would intersect at the point 1, 1. The region then being what is caught between them. This region then, if we were to draw a rectangle in it, would not reach all the way down to the x-axis. So that when we would rotate about the x-axis, we would produce a washer shape. It would be a disk that would have a hole in the middle of it. If you'll forgive the fact that I'm not an artist. What this washer is essentially one big disk with a smaller disk taken out of the center of it. The good news is that the disks are concentric. So we have a circular disk. It's got a center point around which it's rotated. And then from the dead center of it, an inner portion, an inner cylinder is removed. The volume of this then is simply the volume of the full cylinder minus the volume of the disk that was removed. We should probably recognize this from the area between two curves, where instead of the region going all the way down to the x-axis, it was bounded from below by a separate function. We have that same effect here, where we have one function providing the outer radius, while another function provides the inner radius. So the volume here is going to be the volume of the full disk minus the volume of the smaller portion that is removed from the middle of it. If we factor out the common pi and the common h, we arrive at this, where r is the outer radius, the radius of the full disk, and little r is the inner radius, the radius of the smaller portion that has been removed from the center of the full disk. Much like the area of a region between two curves, the outer radius is the one that is larger. Now that can change depending on the region and the axis of rotation. So we need to be careful and make sure that we're not using top and bottom functions like we might have in the area between curves. We need to use the phrases outer function and inner function. Thus, the volume is going to be given by pi times the outer function, f of x squared, minus the inner function, g of x squared, times delta x. To apply the integral to it then, it would be the integral from a to b of pi times f of x squared minus g of x squared dx. This is the formula for the washer method. It is an extension of the disk method that simply allows for the subtraction of an inner function. We did not have that in the disk method because there was no inner portion removed. The inner radius was essentially 0. This is example 3. Let's use the function that we were just looking at. Let's let R be the region bound by the graphs of f of x equals x squared and g of x equals the square root of x on 0 to 1. And then let us have that be rotated about the x-axis. I won't draw the picture again. We just did that a moment ago. The volume of this then would be the integral from 0 to 1 of pi times x squared minus the square root of x. Excuse me, I have that completely backwards. The square root of x squared, that is our outer radius, minus x squared, that is our inner radius, dx. As usual, we can choose to bring the pi in front of the integral. Inside, we can clean this up. The square root of x squared is x, and x squared is x to the 4th. The antiderivative is then x squared over 2 minus x to the 5th over 5, evaluated at 1 minus the evaluation at 0. Of course, 1 to any power is 1, and 0 to any power is 0, so that we have pi times 1/2 minus 1/5 minus pi times 0/2 minus 0/5, which of course is entirely 0, and that entire second portion of this is gone. A quick bit of arithmetic then will give us 3/10 times pi, or 3 pi over 10. Once again, no good way to check this. We can put it in our calculator, but the entire assumption is that our region has been defined properly, so that our integral has been defined properly. And in this case, it is especially important to make sure that we have, since we're dealing with two functions, that we have them in the correct places. The outer radius has to come first in the subtraction, and the inner radius has to come second. One more example. Just as the disk method can be adapted to do something in regard to y, the washer method can also be adapted for something with regard to y. So in this case, let's let R be the region that is bound by the graph of y equal to x squared plus 1 the x-axis, which is y equals 0, the y-axis, which is x equals 0, and the vertical line x equals 1. And we're going to rotate that region about the y-axis. X squared plus 1, let me space that out a bit, x squared plus 1 would be a parabola that starts with its vertex at 0, 1, and then goes up to 1, 2. We also have x equals 0 being the vertical axis, x equals 1 being another vertical line, and y equals 0 being the x-axis. So our region is enclosed here. And then this region is going to be rotated about the y-axis. Now, depending on where our rectangle is drawn, we're going to have two different things happen here. Because we're rotating about the y-axis, we're going to have to integrate with respect to y, which means our rectangles are going to have to be drawn horizontally. However, depending on where the rectangle is drawn, we're going to have two different situations occur. When the rectangle is drawn higher up here, we will have a washer situation. When it is drawn further down, we will have a disk situation. So we're going to have to split this into two different regions. We're going to have to do one region when the y values go from 0 to 1, and then a second region where we will have to use washers when y is between 1 and 2. The reason being that we have an inner radius when y is between 1 and 2, and that inner radius is given by the function y equals x squared plus 1, which we will have to invert. A square root here, which will result in a plus or minus, but because we are looking at a region where x is entirely positive, we can drop the negative sign. So we're going to have to do two integrals here. From 0 to 1, our integral is of pi times, well, 1. On that region, the sideways height of the rectangle is always 1. Every single disk in that region is going to be identical in how thick it is and how wide it is. On the second portion, from 1 to 2, our outer radius is again given by 1. But our inner radius is governed by the curve y square root of y minus 1. So fortunately, these will be relatively simple to work with. The first integral, from 0 to 1 of 1 dy. The second integral, from 1 to 2, of 1 minus y minus 1. Be careful because of the subtraction. Be careful to keep the y minus 1 still in parentheses until we distribute the negative. that will result in 2 minus y dy. So our first integral is easy enough. The integral of any constant is that constant times the variable. Our second integral then would have the antiderivative 2y minus y squared over 2. Our first integral then, after the fundamental theorem of calculus, would result in simply pi. Our second integral would be a little bit more complicated. We would have 4 minus 2 in the first set of parentheses, and then 2 minus 1/2 in the second set of parentheses. This would give us 2 minus 3/2, which is simply 1/2. Giving us a total of 3 pi over 2. So again, we have the disk method, which deals with a solid, cylindrical, flat cylindrical disk that is defined simply by an outer radius. The inner radius is essentially 0 because the base of the rectangle would be against the axis of rotation. But if there is a second function that prevents the bottom of the rectangle from touching the axis of rotation, this will result in a washer, a flat cylindrical disk with another smaller cylindrical disk taken out of the center of it. Thus we have, in conclusion, the disk method which will be either from x equals a to x equals b of pi times f of x squared dx, or the volume from y equals c to y equals d of pi times f of y squared dy. The washer method, the volume with respect to x would be from x equals a to x equals b of pi times f of x squared minus g of x squared dx, where f of x is represents the outer radius, and g of x represents the inner radius. This also is adapted for integrating with respect to y. Now, this assumes that the axis of rotation is always the x or y axis. This can be adapted through being very careful for an axis of rotation that is any horizontal or vertical line.